right, in this second section, we're going to specifically start looking at sound waves. And as I mentioned in the first video for this module, while transverse waves and light waves go together, sound waves are always longitudinal waves. So the longitudinal wave, the diagram that we drew back in the first video, that's where you've got your compressions and your refractions. So things are vibrating back and forth. As the sound wave travels, if it travels this direction, then the particles are going to be vibrating parallel to that direction of motion. So I've got 4 specific properties of sound waves up here on the board that I want to go through with you. The first one, again, sound waves are longitudinal waves. And secondly, the frequency of the sound wave is going to determine the pitch. Now, pitch is what we hear as far as how high something sounds or how low something sounds. So just in general, a woman's voice has a higher pitch than a man's voice does. A piccolo has a higher pitch than a flute does. And so those higher pitches are going to correspond with a higher frequency. Now, if you recall, we said that the velocity of a wave is equal to the frequency times the wavelength. So what that means is that a higher frequency, which means a higher pitch, therefore also means a smaller wavelength. And so if you think about the difference between a piccolo and a piccolo is a very, very short wind instrument, wind instrument. And so as you think about how short that piccolo is, the sound is moving through the piccolo, and the length of the tube is going to determine the wavelength. So if you shorten up the wavelength, that means your frequency is going to go up, and that means your pitch is going to go up. Now, a flute is much longer. And so because the tube that the sound is moving through is longer, that means your wavelength is longer. And so conversely, if your wavelength gets longer, that means that your frequency is going to go down, and so therefore you're also going to hear a lower pitch coming out of a longer instrument. Okay, so sound waves are longitudinal waves. The frequency determines the pitch. Thirdly, the amplitude determines the volume. I mentioned when we started talking about waves, and we talked about transverse waves in the first video, I said, the higher the ocean wave, the more energy it has. And so, if you've got small waves lapping at the beach, they're not going to harm anything. But then if you've got, a big tidal wave, if you've got a big tsunami that comes through and you've got huge waves coming in and crashing, they can do a lot of damage because of the energy that they contain, because the amplitude of those waves is so much higher. Same thing is going to be true with sound waves. The amplitude of those waves is going to determine the volume that you hear. And as the amplitude gets greater, it's carrying more energy, and therefore the volume is going to go up as well. So if you have, maybe you're hitting on something metal, maybe you're drumming on something, and the harder you hit it, the more energy you're giving it, and so therefore the higher the amplitude of the sound waves is going to be, and the louder that they're going to be. Okay. Fourthly, as temperature goes up, the speed of sound is going to go up as well. If you think about this, the speed of sound as it moves through air has to translate from one particle to the next particle in order to travel. Because as we said before, waves have to have some sort of a medium to travel through. You can't hear sound in outer space because there's no air for it to travel through. There's very, very few air particles in outer space. So as the temperature goes up, and hopefully you learned this in chemistry class, as the temperature of a substance goes up, its particles move faster and faster and faster. And so if the particles are moving faster, it would only make sense that as the sound begins to move through those particles, if the particles are moving faster, they can transfer the energy from those sound waves faster as well. And so as temperature goes up, the speed of sound is going to go up. And he also gives you in your text a formula for determining what the speed of sound is going to be. And this temperature in this particular equation is always going to be in Celsius. So you want to make sure that you don't try to stick a Fahrenheit temperature in there. Make sure that this is always in degrees Celsius when you put it in. So 331.5 plus 0.606 times the temperature in Celsius, and then that will give you an answer in meters per second. So let's work a problem with that. Example 11.1. The problem says when someone sings a standard A, the frequency of the sound wave produced is 440 hertz. If the temperature of the air is 25 degrees Celsius, what is the wavelength of the sound wave? So if I go over here to work this problem, what did they tell me? Well, they told me that the frequency is 440 hertz, and I know that the temperature of the air is 25 degrees Celsius, and then I'm being asked what the wavelength is. Well, in order to find the wavelength, I'm going to have to use velocity equals frequency times wavelength. That's the only equation I know that's got wavelength in it. But in order to do that, I'm also going to have to find out what the velocity is. The velocity can be found from this equation down here. So this is the equation I will use first to find out the velocity of my sound wave. So my velocity is going to be 331.5 plus 0.606 times 25.0 degrees Celsius. And you don't have to write the degrees Celsius on here. We're just going to, we know, I've already said we know that that's what that's going to be. And then when I get done with this, my answer is going to be in meters per second. So when I calculate that all the way through, you're going to have to watch your significant figures on here. When you multiply these two together, you're going to have 3 significant figures, and then you're going to be adding after that. So watch those significant figures and make sure you're following the correct operations as you're going through and doing that. So when I multiply all of that through, I'm going to get an answer of 347 meters per second for the velocity of this sound wave. Now that I know the velocity, now I can go back and I can calculate the wavelength, because since velocity equals frequency times wavelength, I'm going to use this equation. So 347 meters per second is going to be equal to the frequency, which is 440 hertz, or 440 per second, times the wavelength. And so then when you divide this through, 347 divided by 440, you will get a wavelength of 0.789 meters. Okay? So that is how you can use those two equations to solve problems with sound waves.